We have one last side issue that we need to cover before we can fully treat the integrands for the mass matrix and stiffness matrix. The domain of orthogonality for the Legendre polynomials, and therefore by extension our orthogonal Gauss-Legendre Lagrange bases, is from -1 to 1. However, our elements could be arbitrary sizes, so we'd like to ideally transform a particular element with bounds xl to xr to some computational domain that's bounded from -1 to 1. We do this by means of a mapping, so we could map from the computational domain to our physical domain, and likewise we have an inverse where we can map from the physical domain to the computational domain. So it's easy enough to construct the mapping functions for this. So if we were to put in, let's say, the far extreme left in the computational domain, so -1, -1 plus 1 is 0, so clearly then this is 0, and we're left with just xl, and similarly if we put in 1 here, this value is 1, so we have delta x plus xl, where delta x is xr minus xl, so we recover xr, and likewise the inverse mapping. So in order to be able to use the domain of orthogonality, we can apply a change of variables to accommodate for the mapping. So here we have some inner product of two Lagrange bases across a domain from xl to xr. We can map this to our computational domain over the explicit domain of orthogonality. However, in order to do so means we're going to have to introduce an additional term. This term is the derivative of the mapping from the computational domain to the physical domain, and this is called the determinant of the Jacobian matrix, or sometimes just the Jacobian for short. And in our particular case, it's easy to see that the derivative of this mapping here is just simply delta x over 2.